This is a review of sampling distributions. So the main idea is anytime we look at a population, there are going to be thousands or millions of possible samples we could take, and each of those samples will be different from the others. So we're going to look at a couple applets. The first one is we're going to draw a sample of n equals 40 pieces from a large population with 50% orange and count the percent of orange that we get. So for this applet, you can see they have a big candy machine. Again, 50% orange. We're going to draw 40 candies at a time, and we can look at one sample. So it's going to do this slowly. But the idea is we are drawing candies from the machine, okay? Or we take a population and we pick out one sample. So after we pick out this one sample, you'll notice that we have a p hat equals 0.70. And there's our little p hat, or our sample proportion of 0.70. Now if I did this a few more times, and I draw another sample, notice my different sample will give me a different sample proportion. So this one was 0.5. That first one, 0.7, was actually really high. I can keep drawing more samples, and every time I draw another sample, I get a different sample proportion. So let's speed this up. Let's try and do 100 samples. So you can see these are all the different sample proportions we've got. And because my sample size of 40 is still fairly small for proportions, you can see I'm even getting some as big as like 0.75 or as low as 0.3. I can draw more samples. And let's see what happens if I draw, say, 10,000 samples. Notice now when I draw 10,000 samples, this looks like a normal curve. So it looks like a normal curve, and it's centered precisely, it's hard to tell because I did a weird scale here, it's centered precisely at 0.5, which was the probability of orange. So if we look at all the possible sample proportions, if we did this thousands and millions of times, the shape ends up looking just like a normal curve. And the mean for all those possible sample proportions, so we'll do the mean for all the possible sample proportions, we use this notation, which is equal to the original population proportion. So the mean of all the sample proportions equals the population proportion P. In this class, anytime you see a hat is always going to mean that that is our sample proportion. And the sampling distribution will just be the distribution of all the possible sample proportions. Now in that example, we cared about proportions. We could also do sample means. We could do sample standard deviations. We could do our sample medians. Anything you can think of, you can find the distribution for. So let's look at a different applet. Let's see what happens if we draw a sample of n equals 25 from any population and look at the sample mean. So this is a nice parent population that started off fairly normal. I can draw a mean from a sample of 25, or draw a sample of 25 and look at the mean. So I can do the animated, but that's going to take a while. So let's try just like 5 different samples. So for 5 different samples, I had a few different sample means. I could try 10,000 samples, and notice it looks fairly normal. And even at 100,000, it looks normal. Now the reason this looks weird is because I didn't put very many pixels on, so they can't actually draw it looking normal. But it ends up looking normal. You can fit the normal curve and see it looks fairly normal. Again, they just don't have enough pixels. Let's look at a couple things. Let's look at the mean. Oops. And standard deviation of these. So my parent population had a mean of 16, and my sample, or the mean of all the sample means, was 16. For the standard deviation though, my standard deviation of the parent was 5, but the standard deviation of all of the possible sample means was only 1, and you'll notice it does look a lot skinnier than that parent population. And that is always the case. We'll talk about that when we switch back to our notes. But let's look and see what happens if we do a different population. So I can make this population look like anything I want. So this is clearly not normal, or I can even do it the other way. No, I was going to try and do something, but I'm not quite artistic enough. I could look at 100 samples and notice it still looks normal. This time we're spread out a little bit more so you can see that it's a little more normal. Okay. Again, let's see what happened to our means. So mean of the parent population is 16.48. The mean of all of those possible sample means, which we only did 100,000, not millions of them, was about 16.48, almost. But the standard deviation got smaller again. So when we look at all the possible samples, the shape is going to be normal. And due to the central limit theorem, we know for averages, if n is at least 30, or 25 is really pretty close to, if n is at least 30, it's going to look normal. The mean for all the possible sample averages, so the mean for all the possible sample averages is just going to be equal to my population mean mu. And the standard deviation of all the possible sample averages is going to be equal to our original population standard deviation over the square root of n. And we can figure out the sampling distribution for a lot of different statistics. Sometimes this involves mathematical proofs. Sometimes it's simulations or visualizations. But anything you can calculate from your sample can have a sampling distribution, because every time you take a different sample, you get a different result for your sample statistic.